So let's start doing an explicit solution. Now that we've thought about it qualitatively a little bit. Of course, we've talked already about how y of t equals 0 if t is less than a, really less than or equal to a. Here's that time a. And so what we can do is just think of it as a new initial condition problem, initial value problem, where we just look at the initial condition at a being, of course, y of a equals y prime of a equals 0. Before the forcing happens, nothing's happening. Nothing is turned on. Okay? And we've got our equation, oops, my double prime plus, and I've conveniently written this again as m omega squared, anticipating that that's going to be a useful way to write it, equals, and now it's just equal to a constant as long as we're between a and a plus delta t. We've got, this is just j over delta t, a constant. Okay, so remember, this is where you really want to know the basics of the ODE stuff. The homogeneous solution, if this was 0, of course, is there's various ways to write it. Sometimes you want to write it as a cosine with a phase shift, or a sine with a phase shift, or just a sum of cosines and sines, and that's how I'm going to write it. And the hint that I put in the PDF was, I should probably erase this, but we'll see. It's going to be helpful to write it shifted, at least so that we're sort of starting time at t equals a. Otherwise, it's just going to be much prettier if we do that. Okay. Again, kind of a symmetry principle that we're allowing ourselves. We know that we can always shift back and forth in these solutions. So a little bit of use of symmetry. Let me go ahead and erase that part because we don't really need it. Okay. And then, so that's a homogeneous solution. And then we need the particular solution. This is pretty much the simplest case of undetermined coefficients. If this is just a constant, then our guess is maybe a constant works. Okay, and that's easy to plug in. You plug in yp into here, that dies, and we get m omega squared. Yp is, c, our mystery constant is j over delta t, and so c is j over m omega squared delta t. Okay, and so our full general solution, we haven't matched the initial conditions yet, is that plus, I'll just put plus yh, plus this stuff. And now we have to figure out the a and the b. Well, that's pretty easy from these conditions. Where can I put it in? I'll put it in right here. It's not the world's biggest blackboard or whiteboard or whatever. Okay, and so this, when we plug it in here, we're going to get y of a, 0, is this constant, m omega squared delta t again, plus this guy evaluated at a. And this is where the hint is really helpful, that this is where it simplifies things a lot. If t is equal to a, the sine is going to die, and the cosine is going to be 1, and so this is just plus a. And so that tells us what a is. I want to keep this. Strategically erase stuff here. Okay, so a equals minus j over m omega squared delta t. And then b, or well, hopefully by plugging in this initial condition, we'll find b. Okay, hopefully it's not too weirdly organized here. Then 0 is going to be the derivative. Okay, now that just dies. It's a constant. This turns into a sine, and when you evaluate that at 0, because again, when t equals a, this is going to be cosine of sine of 0. It's going to die. And then we're going to get omega times b times cosine of 0. In any case, that's 1, so it's going to be 0 equals omega b, or in other words, b equals 0. So we don't need b. Okay, so now we can plug this in. This is going to be minus that same factor, so that's going to be a common factor. We'll write that in a minute. Cosine omega t minus a. Okay, so let me clean that up. I'll erase the whole thing. We get y of t is this master factor, and then it's just times 1 minus cosine of omega. I'm going to not put a parenthesis there. it's the usual sloppy style for like cosines and sines. It's the cosine of all that. So it's sort of technically you need parentheses around that, but hopefully that's clear. Okay. So there's our explicit solution. There's a formula for explicit solution. Of course, that's not really the best way to understand it a lot of the time. Let's look at the graph of that thing. It's not very hard to graph that. So again, syncing it up with the forcing function, this is f. At a, you're going to start with a 1 minus cosine times a factor. Well, 1 minus cosine starts at 0 and goes up to 2. And so it's going to go like this. It's going to start at the bottom of the cosine here. And this isn't really going on because it hasn't activated at a, but I'm just illustrating. It's the bottom of a cosine wave. And that's crucial to match the initial condition correctly because we want this to have value 0 and derivative 0 at this time. So here, it's not the mass is not doing anything, and then you start pulling on it. It doesn't immediately go anywhere. It doesn't have a discontinuous jump in position. It doesn't teleport. And it also, at least with this particular forcing, it doesn't immediately have a velocity. You're giving it some non-zero acceleration very suddenly. The second derivative goes from 0 to non-zero. This has a non-zero concave up, but it's still continuous and differentiable. The first derivative is 0 right at that instant. The velocity is still 0. And then the acceleration takes hold and you get a non-zero velocity. Now, I went ahead and extended this forever. Whenever this turns off, this is going to be false. So it's just going to go to here, and then we're going to have to see what is really going on after that. Now, maybe if you leave the delta t, if the delta t is big, and this is going on for a long time, it will bounce back and forth like this for a while, and then do something new when the forcing turns off. But we're most interested in when delta t gets very small, so it's more like a hammer blow. But we'll get to that. Okay, so this is a good picture, and it's really this part that's really going to be the most relevant part of that picture. Okay. And of course the top here, if we care, we're not really going to let it get to its maximum, but it's just going to be the 2 that comes from here times this master factor. And notice what's going on. The bigger the impulse, the more action is going to happen, of course. Bigger the mass, the smaller the action is going to happen. It's all proportional to the mass. It's going to be more sluggish. The omega squared on the bottom says that if it's a stiffer spring, has a higher natural frequency, then that's going to suppress the effect of this. That's not, I think that's much less obvious. And then of course the J over delta T actually was the force that you're applying. So it's also inversely proportional to delta T. And it's going to be very interesting how that shows up when we let delta T go to 0. Okay, so we're getting some progress here. Okay, so now we're going to look at the third interval. We're going to look at a plus delta t on to infinity. What happens when we turn that forcing off? So this, of course, is, so far we've done it just for a, between a and a plus delta t. And we could put equals or not here. It's going to be a nice continuous function, so it doesn't really matter. So I'm not going to worry about it. Okay, so now, again, we're doing this in kind of a clunky way, and we're going to see after the fact that we can do it in a less clunky way. But we're going to look now at why. Let's use this function to determine the initial conditions on the next segment. So y of a plus delta t, let me get my cheat sheet here ready. Okay, so that's going to be j over m omega squared delta t times 1 minus cosine of omega, and now a plus delta t minus a is just delta t. Okay. Y prime, the constant part goes away. A minus cosine turns into a plus sine. Chain rule brings an omega down. That's going to be j over m omega delta t, not omega squared. And that's going to be sine with an n, not an m, of omega delta t. Okay. And now the differential equation is back to being the homogeneous one. So there, our initial conditions are now quite a bit more complicated looking, but we'll deal with them. But the forcing is gone, and so it's just homogeneous. Okay. So now, again, as per the hint, I'm going to take the risk of erasing the picture. we're going to say the homogeneous solution, which will be the solution here, is of the form something times cosine of omega times t minus a plus delta t, two parentheses. That's kind of squished in there, isn't it? Plus, let me give a little more room for the sign, t minus. So we can always write these with an arbitrary shift, starting wherever we want, as long as we have the a and the b to match the initial conditions. Okay, and once again, it's going to be much prettier if we do that. Okay, so matching up the initial conditions. So if we put in t equals a plus delta t, this just becomes 1. And so we get a is equal to all this stuff. You know what? I'm going to cheat and just say, boom, it's that. It's just y of a plus delta t. Okay. And then very similar to what we did before, when you take the derivative, then this becomes a sine, and when you put in t equals a plus delta t, this dies. Here, this becomes a cosine, but an omega comes out. And so once again, exactly like before, omega b is going to be equal to that puppy. Okay. And this is, I'm sorry, this is really an omega. No. Yeah, that's right. Okay. Yeah, and then when we divide by omega, it becomes back an omega squared. Okay. So let's write that out. It's going to look a little messy at the start, but then we're going to get what seems to be kind of a miraculous simplification. But it's not miraculous. Okay, so y of t. This is only for t beyond a plus delta t. Okay. It's that master factor in front of everything. Okay. Times, okay, we're going to get 1 minus cosine omega delta t, that's that factor, times cosine omega times t minus a plus delta t. Maybe I should have called that b. I don't know. Okay, that's 1. Okay, and then plus, just make sure I'm not getting signs wrong or something. Yeah, we're good. Plus, now this has that same factor. Oh yeah, because when I divide by the omega, that's going to be put an omega squared there. So it really is a common factor of j over m omega squared delta t. Then sine of our magic quantity omega delta t times sine of omega t minus a plus delta t. Okay, and then all of this stuff is multiplied by that factor. Okay, so now, cool thing is that if you do a little trig, if you look at the way trig identities work, a lot of this, you've got sine, sine, cosine, cosine. Okay. And with an opposite sign, and so you can write that. That's the sum formula. Okay. So this is going to be, then there's this 1 as well. Okay, so let's separate that out. The 1, ignore the cosine and sine here, just 1 times cosine, just separate that out. That's omega times t a plus delta t. Okay. And then it's going to be minus the sine, and plus cosine, cosine. So I'm going to put a minus in front, and then that's just the cosine sum formula. And what are we getting? We're getting t minus a, omega t minus omega a minus omega delta t, and then plus omega delta t. Boom. Goes away. So it's just omega back, omega times t minus a. Oh, hey. Okay. So this is a cosine of omega t minus a. And then that's all times the j over m omega squared delta t. Okay. So work that out for yourself with the little trig identities if you're not following it. I don't think I want to do it any more detailed than that. But what we get is something surprisingly simple. And interestingly enough, the t minus a shows up even though we were doing everything in terms of t minus the quantity a plus delta t. The end of the impulse seemed to be the crucial thing that was determining things. But the t minus a, which came from the start of the impulse, that's coming back again. And we just get a difference of almost identical terms. Cosine of omega, of course that angular frequency is coming into everything, but basically a cosine of t minus a shift in both of the terms with opposite signs and just the shift that corresponds to the end of the impulse and the start of the impulse, all times the appropriate factor that gives the size of the response to that impulse. Okay, so we really want to understand what's going on with that. Okay, so if we want to write it, okay, there's a lot of mess here, but we'll clean it up for the next part. Okay, we're going to say, so this is what the next part, subpart A. And here's a little exercise. And again, if you didn't already look carefully at the whole PDF, whenever you want to pause the video and try the next little step, it's a good idea. You'll learn a lot more. Okay, so it's 0 if t is less than or equal to a. It is j over m1 squared delta t times 1 minus cosine omega t minus a if t is between while the pulse is happening. And then interestingly enough, it's not a lot more complicated once the pulse is gone. And that's a hint that there should be a slicker way to do this. And so we're getting cosine omega of t minus a plus delta t minus cosine omega t minus a. Okay. And I just want to show, part B is about how when you've got these piecewise things, we're dealing with a lot of piecewise stuff right now. And this whole course isn't going to all be about piecewise functions. But when you've got piecewise things, it's nice to be able to summarize that using step functions. So what we can say is this ubiquitous factor in front, maybe I should have had a quick notation for it, but whatever. Okay. Times, you can call this big parentheses, and then 1 minus cosine omega t minus a. So we're going to turn that on at a. Okay. And then we want to turn that off and turn on this guy at a plus delta t. Okay. Well, the thing is, though, we want to leave the minus cosine omega t minus a alone. It actually is part of this. So we just need to turn off the 1 and turn on this guy. So we're going to subtract a very similar term, exactly a shifted version of that term. Okay, one more parenthesis, I think, yes. Yep, okay. And then times the step function that turns on at, and then one more parenthesis. So this is the step function that turns on at a plus delta t. Okay, and so this really is really suggestive, and we're going to see why this is of this form. This is literally, this thing here with this factor is a certain function of t. This is exactly that function delayed by delta t. And it's just the difference of those two guys. Okay, so you might want to think already, if you haven't looked at the next part of the PDF, why is it so simple? We didn't do it in a way that made us necessarily expect that. We did it tracking along 0 and then something and then another influence, and you just think that this is the most complicated thing because it combines this influence and this influence, and it's nice. It'll be nice to see why this is so nice and simple. Okay. Let's look at the graphs of these guys. I'm going to go ahead and bring on the computer version of this. Let me just make it a little smaller here. Oh, it's not resizing very well. Okay. So let's see, maybe a little bigger. Okay, so for example, with the example in part 4, where we have delta t being much longer than we're eventually going to look at, we get, it starts out here, and it's a little hard to tell that it really has zero derivative here, but it really does. This is just the scale doesn't make it obvious. Starts out as the 1 minus cosine, does a few oscillations, and then right around in here at 13, it switches and then comes back and oscillates in this way. And notice that when the forcing is on, it's going around a new equilibrium. When you stretching the spring out, it has some residual bounce from what happened, the fact that you started the stretch suddenly, but it's really trying to go around an equilibrium that's at 0.1. Because if you actually had constantly had a force of 0.1 Newton in this system, then it would just, if you look at the constants, it's just going to have an equilibrium of y equals 0.1. Then you let the forcing go, it's going to want to oscillate around the actual equilibrium because you don't have the forcing on. And it's just going to fairly smoothly interpolate here. It's pretty hard to see. This is, unless you think about it a bit, this is not twice differentiable here. It's actually going from decently up, concave up to concave down. But it is continuous and differentiable. The velocity doesn't change suddenly. Now, if delta t equals 0.1 seconds in part 5, that's much more like what we're interested in the later parts where we want to send delta t going to 0. Here, you can see just barely at the start, for 0.1 seconds, it's concave up. It's actually kind of hard to see even in the picture. It's just starting from zero derivative, concave up, but then suddenly, it actually kind of looks like a sine function. If you didn't look at the little tail here where it's concave up, it actually just kind of looks like a sine function, starting from its natural starting point, 0, and then going on its merry way. Well, that's interesting. We haven't written down any sine functions as the solution yet, and that's going to be interesting to see where that comes from. If you look, if you look at a zoom in of that, you can see it starts with zero derivative, comes up concave up, but then at 0.1, you turn that forcing off, and now the restoring force is going to start making it concave down. It's going to start pulling it back. Now it has a very significant velocity upward. The y prime is still forcing it away from the equilibrium for a while, but the restoring force is making it concave down, and eventually is going to pull it back. And indeed, it pulls it back eventually to oscillate around 0. Okay. All right, that's plenty of stuff for this video, and we'll continue with this PDF in the next one.